So I'm going to talk about quantum optical devices with interacting Fermi gases, and this talk is going to be about ultra-cold atoms. And since I'm the first speaker of this conference to deal with this topic, before I explain you what this picture actually represents, I'm going to explain a little bit about quantum gases, in particular, what's the differences and what makes them distinct from electronic systems that you are probably very used to. So the first important aspect, which is going to be critical for what I'm going to talk about, is the way atoms couple with light. So atoms interact with light by dipolar interaction. And if you send resonant photons onto the atoms, the photons are very efficiently scattered. If you send light that's off resonant with internal transitions inside the atom, what you're going to get is an atom that's polarized. And to second order, this polarization gives rise to a potential that's proportional to the square of the electric field, so the light intensity. The consequence of this is that any light intensity pattern you can create directly maps onto a potential that is seen by the atoms. And we're going to think of the atoms as sort of particles which we will use to mimic electrons in some solid state structures. And the way we are going to engineer the potential landscape is by optical methods. And this is particularly handy because we deal with very dilute systems for which the Fermi wavelength is of the order of the wavelengths of visible light. And therefore, we can create structures and we can observe and manipulate the atoms at the scale of the Fermi wavelengths using microscopes and optical methods, which I'm going to detail a bit further. That's the first very important aspect. The second, of course, is that atoms are actually charge neutral. So they interact by the van der Waals potential, which for all practical purposes for our densities and temperature is actually a contact interaction. This contact interaction is controlled by the solution of the two-atom problem, which is in turn controlled by the internal structure of the atoms. Atoms are complicated particles, they are composite, they have a lot of internal degrees of freedom, and as a result, the molecular structure that we get for the two-atom problem can be controlled by external fields. And typically what we do is we place atoms in an external magnetic field that has no orbital effect because the atoms are actually neutral, but what it does is it shifts the molecular structures around. And using this, we can create scattering resonance by bringing one molecular state very close to dissociation threshold. The consequence of this is that the parameter that's controlling the two-body interaction, which is the scattering length, that is number A, can actually show a divergence at particular values of magnetic fields. And that's a region where the gas is made strongly interacting. It's strongly interacting in the sense that we have S-wave scattering, which are essentially resonant between particles. It's as large as permitted by quantum mechanics. So this is for the particular example of lithium atom, which I'm going to deal with in this talk. So the interacting Fermi gases I'm going to discuss are ultra-cold gases of lithium atoms cooled down to quantum degeneracy and prepared in the vicinity of this point where the scattering length diverges. And this is something which realizes the so-called BEC to BCS crossover, which means at low temperature, we know that in all this region here, the Fermi gas we prepare is actually a nice S-wave superfluid. And this system has been heavily studied in the past, starting from the pioneering work of David Jin, actually very close to here, and then it's been taken over by several groups over the last 15 years. And we know really a lot about this system, in spite of the fact that it is very strongly interacting. We know, we are pretty confident, we know the phase diagram, we know most of the thermodynamics, we actually even know now quite a lot about response functions, both from theory and from experiments. So the way I want you to think about this is that this is sort of a bulk material with no lattice, by the way. This is important because all the things we think we know don't apply in the presence of an optical lattice. But in free space, we know really a lot about this. So think of it as a sort of bulk material over which we have a large degree of control. So what this talk is going to be about is basically what kind of evolution we can think of when we start from this bulk material and we want to add sort of new layers of complexity. And I'm going to focus on two aspects. The first one is trying to take this material and shape device-like systems in the spirit of mesoscopic physics that was very nicely introduced in the previous talk. And there I will present one result we have obtained in 2018, where we study transport in an array of sort of point-like scatterers that's implemented on this strongly correlated Fermi gases. And the second type of layer of complexity which we want to add, and that's something which has been going on in the last couple of years in my group at EPFL, is interfacing these systems with photons. And basically, what I'm going to tell you in this part, if time permits, is that we are now capable of taking these Fermi gases and doing cavity quantum electrodynamics with this in the single photon, single atom strong coupling regime. So let me start with the first aspect. So these are experiments. Oh, I'm sorry for the. These are experiments which were carried out at ETH Zurich in the group of Tillman and Esslinger. And this is a joint theory and experiment project together with our chairman and his former postdoc, Piotr Grishin. And there the idea is that we have this cloud of fermions, and we would like to mimic the behavior of mesoscopic devices. And the way we do that is we start from a cloud of atoms that looks like this. It is CR-shaped. That simply reflects the fact that it's trapped system, so it's trapped in vacuum, and then we use a combination of laser beam to give it this shape. And then on top of this, we just shine a number of laser beams that intersect, that intersect the cloud here at the center. So over a small region here, which is about 1/10 of the length of the cloud, we have very tight constriction, where the transverse trap frequencies or the level spacing here is much larger than the temperature. And that creates a one-dimensional channel connected to large chunk of cold atoms here, which looks a lot like the textbook two-terminal Landauer system. And once we're equipped with this system, the only thing we do is we prepare it with a little bit more particles in one side than in the other. We wait as long as we can, which means a couple of seconds before temperature goes up and the coil don't like that. And we just measure how many of these extra particles have made their way through. And we do that simply by imaging the total number of atoms on one side and in the other simultaneously. And that gives us the information on the current. And if now we know the equation of state of the two reservoirs, we can connect these extra particles we have added to chemical potential difference, divide current by chemical potential difference, and get a conductance. So when we do this with this simple structure that mimics a sort of quantum point contact, we get this kind of curve. So this is something we obtained in 2015, where we see basically quantized conductance, exactly as expected from the Landauer formula. So this is the Landauer formula without any fit parameter. So that's really nice. It's the first time that this quantized conductance was observed with neutral matter. It's also very nice for us because it tells us that this protocol I described you actually measures the conductance you would expect if you had electrons. So this means we really have a one-to-one correspondence between what you could do with the mesoscopic physics apparatus and what we do now with ultra-cold gases. And we have studied this kind of system extensively. Again, with interactions, we've measured spin conductances, actually even heat conductance, and so on. And we wrote a short review article about this if you're interested in the details. So what I'm going to discuss now is what happens when you take this guy here and add something which is a mesoscopic lattice. That's basically, we take this one-dimensional sort of short quantum wire, and on top of that, we project in a deterministic way a set of barriers, which you can think of as a sort of point-like scatterers. They are very weak. So basically, the main thing they do is when particles are incident on them, it's quantum reflection, right? This is not really tunneling at that stage. This structure is actually very weak. But that's enough for us to see quantum interferences in the sense that if we make an array of these, say, for example, 9 of these obstacles, what we see is basically a band structure, right? This is stupid Bragg scattering, this sort of quantum mechanics 101. So this is the curve conductance as a function of gate potential, but this stands for chemical potential inside the structure. This region here is a regime where the entire structure is empty, and as we increase the potential, we see the conductance go up. And there's this dip here, which is exactly where we expect the band insulator to sit. There are several things you see on this. First, this is very smooth. It's very far from what you would expect from semiconductor physics with band structures, where you would have conductances that sharply drop down. This is due to finite temperature. And this is the main enemy in everything I'm going to tell you about. So this finite temperature is actually smoothing everything. This is something we understand quantitatively pretty well. The other thing which I will talk about in the second part of the talk is the error bars here, which, in unit of the quantum of conductance are a bit ridiculous compared to what you can do in electronics. And I will come to that because we have ideas on how to improve this. So this is sort of the starting point. That's what you get for weakly interacting particles. And now the question is, which we asked is, what does happen to this if everything else equal, so fixed temperature, fixed density, fixed everything, we increase an attractive interaction, right? And we increase it up to unitarity. Of course, at some point when you do that, these leads here are going to get superfluid or superconducting. And the question is, how does that translate into the conductance? And this is something which is very surprising. The answer is nothing happens. These are, okay, so first, this is a detailed plot of what this curve looks like as a function of parameters. I'm going to switch to interactions now. You perhaps don't see it very well, but all these curves here are for different interaction strengths. They span 2 or 3 orders of magnitudes. And what you see is essentially this feature with an error bars is always there. The conductance is quantitatively pretty much the same. And we always have this dip here, no matter what we do. What happens here at high gate potential is sort of the multimode character of the channel. This is something which is much more complicated, which we don't understand very well. But as far as the single mode regime is concerned, it seems that pretty much no matter what we do with interactions, there's no way to get rid of this pattern. That is something which is even more surprising because a couple of years before, we had actually studied the same system without the lattice pattern. And there what you see is that as you increase interaction, this is low interaction, this is stronger interaction. Again, everything else equal, more and more attractive interactions at finite temperature. So the system at some point crosses the superfluid transition. And sure enough, the conductance shoots up. That's not at all what happens. And remember, what we have here is a very weak lattice. It's a set of very weak scatterers inside the channel. And that's something which puzzled us, and that's where we turn to our colleagues from Geneva. And the reason for why this actually takes place is a very nice piece of one-dimensional physics. And the idea is that it can be summarized in this graph. You can describe this interacting system inside the channel as a Luttinger liquid. And now what happens when you have fermions in one dimension with attractive interaction, which we do, actually the attractive interaction is reinforced by the transverse confinement in our experiment. What happens is that you actually form a spin gap such that the charge degree of freedom or the transport properties are controlled by composite objects which are made of these fermion pairs. And now you can think of these fermion pairs either as fermions with attractive interactions that are bound to each other, or as composite bosons. There's a one-to-one correspondence between the two. And if you think of them as composite bosons, you realize that these bosons have a very strong repulsive interaction with each other. It's actually equivalent to a finite range repulsive interaction, simply because these pairs, when they come close to each other, they remember they are made of fermions. Therefore, they have to obey the Pauli principle. That gives rise to the repulsion. And now if you take strongly repulsive bosons in a one-dimensional system, and you know about Thierry's book, you know that basically if you put a very weak lattice that's commensurate with the density, basically this boson will crystallize and the thing is going to form a gap. And that's exactly what happens. This is called the loser embryo liquid as far as the fermions are concerned. And what the picture is then that you have this weak lattice that pins these composite bosonic fermion pairs, these composite bosons. And now you realize when looking at this sort of insulator, that's a very correlated insulator, that if you change the interaction here, say you reduce it to 0, what you're gonna get is always something which has two particles spin up and spin down on each lattice side. And no matter what you do, you can just bring the interaction to zero and the system is gonna cross over directly to a band insulator. This is something completely smooth at commensurability. So no matter what you do, this guy here is gonna stay there and it will be an insulator, whatever the interaction strength. And that's the pattern which we are seeing. So Thierry has put that in mathematical ways. He has modeled our experiment, including finite size, inhomogeneities, finite temperature, and so on. And what you see here is the theory for the conductance close to this point, here for the different interaction strengths we have. And you see that at least qualitatively, the agreement is pretty good. Also in terms of how this minimum is actually shifting a little bit, and the magnitude of the conductance is compatible with what we see in the experiment. So again, the message for this type of experiment is that while we are able to measure conductances in a way that's analog to what you could do with mesoscopic physics, in spite of the fact that we have huge error bars as compared to what we have seen before with electrons, we can access regions of the phase diagram where we have very, very strong interactions, such that you can get actually some surprises and observe states of matter, which as far as we know, this Luther-Emery liquid had actually never been observed experimentally before. So that being said, I'm going to switch topic now and change to the second part of my presentation. And we're going to also change university because this is now a new experiment which I've been setting up over the last 3 years at EPFL. And I want to highlight in particular the work of Kevin Hu, who was bold enough to start his PhD in this lab. And basically in less than 3 years turned it into a nice cold atom experiment, which works. And where we now can really combine a cavity QED with strongly interacting Fermi gases. So the idea there is that we're going to have a high finesse cavity. So this is what this looks like. There are these two mirrors separated by about 4 centimeters. And this is a high finesse cavity. The technical aspect probably you're not really interested in. But the point is that this cavity here is going to use later on to couple single photon with the atoms in the strong coupling regime. The cooperativity here is larger than 1. And in between these two mirrors, we produce strongly correlated Fermi gases. This is a nice example. It's a Bose-Einstein condensate of fermion pairs, which we have observed in our experimental setup. I just want to say that there is quite some technical overhead to try to build this. This is the only experiment of this kind that exists. And so if you are interested in the technical aspect, I can comment on this privately if you have questions. And the cool thing is that it actually works in the sense that we have both now quantum degenerate strongly interacting fermions and single photon coupling. So what we can check is that indeed we reach the strong light matter coupling regime. We do that by simple transmission spectroscopy through the cavity. We have now lithium atoms, so we remember the atomic structure. Our lithium atoms are composed of 2 hyperfine states. So I spoke about spin up and spin down before. What these are actually is hyperfine degree of freedom of the atom. These are spectroscopically resolved. They are separated here by 80 megahertz, which we nicely see by laser spectroscopy. And we just now couple photons to this system, and we have 2 tuning parameters. One is the detuning of the cavity with respect to the atomic transition, and the other one is the detuning of the laser with respect to the cavity. And that provides us with a nice transmission spectrum. And if you know a bit of polariton physics, this is basically polaritons. Right? So you have, because we have 2 atomic states here, plus 1 cavity mode, you expect 3 branches of polaritons. The first one here, which you see nicely, one which is in between the 2 atomic resonances. So on this graph, the atomic resonances are diagonal lines, and cavity modes are horizontal lines. So the upper polariton, middle polariton, and the lower polariton here. There's obviously much more structure in there. We understand it pretty well if we remember that our cavity is a real cavity, so it has not only one mode, but a multi-mode structure. I make this story short. we can make a model for the quantum optics part of this experiment, which includes 120 modes of the cavity. The cool thing with this kind of quantum optics aspect is that even I can do the calculation for the for the optics part, and you nicely recover the polariton structure and these branches which we have here for negative detunings. I should say here, there's no free parameter in this simulation in a sense that all the light matter coupling is calculated from first principle. And this is for independent atoms, of course. And what you see is that what this proves is basically that we indeed have the cavity we think we have, and that the coupling is actually what we think it is, and we are indeed in the strong coupling regime. And so far, the fact that here in this experiment, the atoms are very strongly interacting doesn't really matter. Except if you actually look very carefully. If you look carefully, what you see is that there are a few extra branches here. And this looks like there would be some atomic levels which we forgot in the calculation. Now, of course, there's one thing which we are sure about, is the spectroscopy of lithium atom. And what we know is that there cannot be any atomic level that's in this plate. So what's going on here is that what we account for in the theory, at least in this simple-minded theory that I showed here, is of course single atoms coupled to light. Now, if you put two atoms and think about two atoms scattering a photon, what you can have is one atom absorbing, the other atom absorbing, but you also have other types of transitions. Oh, that's a disaster. But these are transitions by which you take the two atoms, and instead of bringing one in the excited state, you take the two and bring it into a molecular state. This is called photoassociation. It's a venerable field of AMO physics. For lithium atoms, it has been done extensively by Randy Hewlett in the 90s. And this is exactly what we see. And now the cool thing is that the light matter coupling is actually much more complicated. You have actually a situation in which you kill a photon, you take an atom of spin up and an atom of spin down, and you make it a molecule. And what this means is that when you see strong coupling in these transitions, which we do, if we zoom strongly enough, we are actually making some kind of pair polaritons by which we have single photons directly coupled to the pair correlation function. And it's a few lines of math to start from this Hamiltonian I showed you and deduce that the Harvey splitting we observe here is directly proportional to the pair correlation at short distance. That is something which is very exciting because in contrast to the spectrum with coupling to single atom, this coupling to pairs is actually sensitive to interaction strengths. It really contains many-body physics. This is what we observe. If we vary the interaction strengths, this is unitarity. This is so-called BC side or BCS side. And what we see here is that the Harvey splitting is going down as we change magnetic field or as we change interaction strengths. That reflects the fact that the size of pairs is actually changing as a function of interactions. If pairs are very close to each other, it's very easy for them to be turned into molecules, and it's much harder when they are further away. And this is directly mapped onto the spectroscopy of the cavity system. I will just not say much more about this. We now think we have a quantitative understanding for how this actually scales. This is work in progress in the lab right now. With that, I just want to summarize. I showed you a few, one particular experiment in which we do mesoscopic transport. There's much more which we can do, in particular controlling spin transport. This is what's going on right now and my former colleagues at ETH Zurich. And we can really search for new states of matter using this kind of complicated arrangement. And there are many perspectives for this cavity QED experiment with coupling to fermions. I just want to highlight one particular example of this, which is where we actually want to merge the two aspects. It's a proposal we've put together a couple of years ago, where we think we can use this two-terminal system, couple one reservoir to the cavity, and perform non-destructive measurements of the population here. And if you do that, you realize that what you're doing is keeping track of each and every atom entering and leaving this channel. And that should give you the best possible transport measurement ever. And it turns out that you can actually operate this system and derive what the quantum limit to this is. And this system actually should operate in a regime where the resolution is only limited by measurement back action. That is the fact that projecting one of the reservoirs onto fixed atom number is killing the current, just because, well, you cannot have fixed atom number and finite current at the same time. We put a bit of math in that, and it seems pretty promising as a perspective for these experiments. And with that, let me thank you for your attention. We have decent mountains also in Switzerland. You're welcome to pass by if you want to see the lab and discuss at some point.
Thank you, Jean-Philippe. So I guess we start directly with a question. Can you repeat the question?
Sure.
Yeah. So thanks for the beautiful talk. You mentioned that the Luther Emery liquid may have been seen for the first time in your case. Do you have thoughts on what ingredients the cold atom system has that are not available in standard mesoscopic systems, or what is different?
So the question is what makes cold atom, what makes it possible for cold atom to observe the Luther Emery regime that makes it not possible in other systems? I think we have purely attractive interaction here. There's no Coulomb repulsion, and that's just by construction. So I think that's, Thierry, perhaps you have some comment on it, but I would say this is the main point.
Yes.
So I understood that the first thing about the Bose-Einstein condensation was on the side, so you have momentum distribution signature. How do you, I didn't quite get, if there was a signature on the BCS side, at least a BCS.
Okay, so so the question is, how do you identify superfluidity when you're not just on the BEC side?
Yeah, if you're on the other side.
Exactly. So do we have different signatures? So I showed this momentum distribution, that's sort of the canonical way. And to do this, we actually go wherever we like, BEC or BCS, but we do a fast sweep of the magnetic field before imaging. So that sort of maps the system adiabatically to the BEC side. And if we conserve entropy, we kind of know where we are in the phase diagram. That's one way. The other way, which we have extensively used, that's actually the one we use in our paper, is we measure we directly observe pairing. So we put a spin imbalance in the system, and we observe that at the center of the cloud, the spin susceptibility is strictly 0, which is basically meaning that you have a phase separation between a paired core and polarized wings. And this is a signature of superfluidity that's well documented in the literature. That's another possibility.
Other questions?
Briefly at the end, quite interesting. Is there any measurable amplitude you think for a 3-body or 4-body molecular state? In some of these cases, there were actually further higher end states than observed.
Yes, so the question is about this molecules. Is it possible to actually see 3-body or 4-body types of photo association? I think to be honest, the molecular part of this, the exact molecular structure, we don't know, because it has not been calculated in this regime of parameters, and it's actually something which requires a professional molecular spectroscopy. Now, the likelihood that you already have 2 atoms very close to each other is small. So the likelihood to have 3 is actually even lower, especially because that would require to have a spin up and a spin down. So the third is either spin up or spin down, but this is killed by Pauli. Actually, the 3-body processes in ultra-cold atoms, at least for fermions, they are killed by a very large amount that has been calculated many years ago by Juraj Liapnikov. And this is something, so 3-body is something which is extremely difficult to see, at least for fermions. For bosons, this is clearly seen.
Another question or comment? No, doesn't seem to be the case. So let's thank Jean-Philippe again.